Welcome back, and in this lesson I want to talk about hashing, what it is and why we need it. Now we do have a lot to cover, so let's jump in and get started straight away. Put simply, hashing is a process where an algorithm is used to turn this or any other piece of data into this, a fixed length representation of that data. Hashing is at the core of many critical services that you use today, such as passwords, digital signatures, SSL certificates, data searches, and even some antivirus or anti-malware solutions rely on hashes so they can store definitions of malicious files without having to store every single huge file. We even have some forms of digital money such as Bitcoin which use hashing. Now, to understand why hashing is so important, we need to step through how it works, what benefits it provides, and some of the terminology used. So let's go ahead and do that. Hashing starts with a hash function, and think of this as a piece of code, an algorithm. Now there are many different ones which are used or have been used over the years, and examples include MD5 and SHA-2 256. The core principles of hashing is that you take some large variable-sized data and you put that data through a hashing function and receive a fixed size hash of that data. So whether the data is a text file, an image, or a huge database file, the hash you receive will be tiny and fixed length based on the hashing function type. Now also critically, if you take some other data and again put it through the same hashing function, you will get a different hash, a unique hash value. Even if the data differs by only 1 byte, 1 character or 1 pixel, it will result in a different hash. The aim with hash functions is that any change, no matter how minor, will result in a different hash value. Another critical part of hashing is that while getting a hash from some data is trivial, what you cannot do is take a hash value and get the original data back. There's no way to do this. Let's say that you had a hash of an image. Well, you couldn't take that hash and derive the image. You could if you had infinite processing power and infinite time, brute force every image in existence to try and link back to the hash, but this would require hashing every single image until you found the correct one. You should view it as impossible with any modern hashing algorithm to derive the original data from a hash. Without some vulnerability in the hashing function, or without infinite time and processing power, the hashing is one way only. Data through to hash. Now lastly, another fundamental part of hashing is that given the same data, you're always going to get the same hash value if you use the same hashing function. So for one piece of data, you get one hash value. For a different piece of data, you get a different hash value, and hashing is one way only, and you should never get the same hash value for different data, though more on this in a second. Let's look at an example of where hashing can be used, which should be pretty familiar. Imagine you're using an online service and they have a single server. And when you create an account on that service, you create a username and password, and both of those are stored on that server. When you log in, you send your username and password to the server, and an automated process checks the password that you send with the one that's stored, and if they match, you can log in. Now, even if you encrypt your password in transit, and even if the password is encrypted when stored on the server, your password still exists on that server. And it means if the server is ever exploited, then a bad actor will have access at worst to your password and at best an encrypted version of your password. Assuming a full data dump or a long-term exploit, it's pretty trivial to get the plain-text version of your password in this way. And then if you use that password on other services, those services are also at risk. But what about if we use hashes? Well, with this architecture, instead of sending a password to the server when signing up or signing in, we send a hash of the password. This means the server, instead of having our actual password, it only stores the hash of our password. All the server needs to do is check that the hash that you send matches the one in its database, and it can confirm the password was entered correctly on the local client, because given the same data, in this case a password, and the same hashing algorithm, you'll end up with the same hash value. So by comparing the hash value it stores to the hash value that you deliver, i.e. the hash of your password, it can check you're entering the correct password without ever storing a copy of your password. Now on this example I've used the MD5 hashing algorithm, but as you're going to see in a second, this isn't super secure anymore, so you'd likely need to use another hashing algorithm. I'm going to use MD5 as an example to demonstrate a weakness of some algorithms. So to stress, you wouldn't generally use MD5 for production password systems. You choose something a lot more secure. Now if this server was ever exploited when using password hashes, this would be much safer because the hashes are one way. You can't derive the password from a hash. Nothing stops the attacker though from guessing over and over again, trying every possible word and phrase combination with the hashing algorithm used until it guesses right, and then it has confirmed the password that you used, and it can try and exploit other services which you also make use of. And this is why it's really important to use a modern, secure hashing algorithm. Now there are two things with hashing which are really bad. One is if we were ever able to take a hash and derive the original data, but as I mentioned earlier, that's basically impossible without a critical vulnerability in how hashing works. Another major problem would be a collision. An example of a collision is that if we take this image of a plane, and if we hash this image, and then if we take another image, say this image of a shipwreck, and we also hash this image, we should have two different hash values. If we do, awesome. If not, if the hash of A on the left equals the hash of B on the right, then bad things happen because we can no longer trust the hash function, i.e. the hash algorithm. And this is one of the reasons that MD5 as a hashing algorithm is less trusted, because collisions can happen. We can actually show how they can be created, how data can be manipulated to cause collisions. Now I've attached some links to this video with the research project showing how we can create those collisions, but as a quick example I want to switch to my terminal and demonstrate how this works with these two images. So in this folder on my local machine, I have two images, plain.jpg and ship.jpg, and those represent the two images that you've just seen on your screen moments ago. I'm going to go ahead and generate a hash value of one of these files, and I'm going to use the MD5 hashing algorithm. So I'm going to put MD5 space and then plain.jpg. Go ahead and focus on the hashing value that's been generated. So this hashing value, in theory, should uniquely represent the image plain.jpg. So plain.jpg should always generate this hash value, and if I repeat this command, I get the same hash value. But what should happen is if I generate a hash of another piece of data, I should get a different hash value. So I'm going to run MD5 again, this time on ship.jpg. Watch what happens. In this case, it's the same hash value, and this is an example of a collision where two different pieces of data generate the same hash value. And this is a weakness of MD5. We can create this collision. We can adjust the data in order to generate this collision, and this is a bad thing. This shouldn't happen. Now I'm going to follow the same process but using a more secure hashing algorithm. So this time I'm going to use the SHA-2 256 algorithm on this same file, plain.jpg. Now watch what happens now. The hash value is longer because this is a different hashing algorithm, but we confirm that this hash value is for plain.jpg. Now I'm going to run the same hashing algorithm on ship.jpg. This time note how it's a different hash value. This is a much more secure hashing algorithm. SHA-2-256 is much better at protecting against these collisions. It's a more modern and more well-trusted hashing algorithm. Now, just like any other form of security such as encryption, it's important that you always use the latest and most secure protocols and architectures. So if you're using hashing in production, you should generally use something like SHA-2-256, because if you want to guarantee that one-to-one link between a piece of data and a hash, so that any other piece of data generates a different hash, you need to make sure you're using a well-respected hashing algorithm, such as SHA-2-256. Now, the likelihood of this happening in normal usage is near impossible, because these two images have actually been artificially adjusted to cause this collision, but it does represent a theoretical vulnerability in the MD5 hashing algorithm. I've included links attached to this video which detail the research project and some examples of how you can implement this as a personal project if you want. But at this point, I'm going to go ahead and return to the remainder of this video. Now, just to summarize with hashing, you take some data plus a hashing function and you generate a hash value. Now, you can't get the original data from a hash, it is a one-way process. And the same data should always generate the same hash. Different data should always generate a different hash. Now, I've just demonstrated how you can artificially cause a collision using older hashing algorithms, but in the real world, even older algorithms should generate a different hash for different data, and any modern hashing algorithm is protected against even this artificial process. Now, hashing can be used to verify downloaded data. If you're making some data available for download, you can have the download in one location and the hash of that download stored on a different system. It means that you can download the data, you can hash it and generate your own hash value. If the hash values match, then the downloaded data hasn't been altered. If they differ, then it means that what you have is not the same data as what was made available by the original author, and this is a process that's very often used to verify sensitive applications. So if you're downloading any form of application which stores sensitive data or operates on sensitive networks, then you'll generally find that a hash will be made available by the author of that application, and it can be used to verify that that download has not been adjusted. Now, in these type of security sensitive situations, or if you're a security professional, you also need to be sure that the hash itself hasn't been altered, and also whether the hash itself was generated by the person who claims to have generated that hash. So if I make some software available to you and you download it, you need to first check that the download hasn't been altered by hashing it yourself and comparing your hash to the hash that I publish. But you also need to be sure that it was me publishing that hash and that the hash that you download hasn't been altered in some way. And a way that this can be done is using digital signing or digital signatures, and this is something that I cover in another video. But at this point, that's everything I wanted to cover in this video, so go ahead and complete the video, and when you're ready, I'll look forward to you joining me in the next.